Thank you. Okay, thank you everyone for coming to the session till the last day. Today I'm going to talk about how to evaluate an intervention in a two-sided marketplace driven by the recommender system. And this is joint work with my wonderful collaborators, Shichao Han from Tencent, who is sitting here, and Yuchen who from Stanford, who is also here, and also our Zhenling Jiang, who unfortunately had to leave early, but has been really indispensable throughout the whole project. We're going to look at the online content platform named such as TikTok and YouTube, and which has been really successful over the past few years. And these platforms host a two-sided marketplace. Here, the supply side is the creator side, who are responsible for producing a bunch of the content, and the demand side is the viewer side, who are consuming contents. And these two sides are connected by the backend recommender system here. The recommender system is actually the secret weapon of these companies, and which really drives the success behind these companies. And the recommender system can increase the short-term outcomes, such as the traffic on the platform, as well as the long-term user engagement. As the quote here says that the recommender system actually helps us to know ourselves better, which means that it really revolutionized the way of how we get information from the massive amount of data here. And let's take a closer look at how the recommender system works. The platform actually hosts a very huge content pool, which consists of billions of content items here. And when a viewer comes, the recommender will be responsible for selecting one content tailored to the particular viewer preference. And the whole pipeline here is actually pretty complicated in the industry. It consists of a lot of machine learning algorithms. But roughly, it can be split into two phases here. The first phase is the retrieval phase, which is responsible for selecting a collection of the content items from the content pool the viewer may be interested in. And and this is what we name as the consideration set here. And the second phase is the ranking phase. And during the ranking phase, the recommender is going to evaluate each content more thoroughly and then picks the one for the incoming user here. And the whole process here is personalized, which means that both the constraint set can be different from person to person, as well as the exposed content here. Okay. Since the recommender is really important, the companies are seeking different ways to optimize the recommender system. For those, the updates of the algorithm we name as a treatment, which will essentially change the way of how the content gets recommended from the consideration set. And during the ranking, specifically, we're going to focus on the ranking phase, which means that we will change the way of how recommender evaluates different content items here. And ultimately, that will change the likelihood of one content item being exposed to the incoming viewer. And this quantity we term as the exposure probability here. And we're going to focus on the treatment that are targeting at the creators in our work. This kind of treatment can include for example, the Causal algorithm, which intentionally boosts the traffic of the small creators such that they can get more exposure on the platform. They can also include some promotion algorithm such that the creators who actually pay to get more promotion will get more traffic. And accordingly, we're going to evaluate this treatment or the update of the algorithm using the creator side outcome. And here we're going to focus on the engagement metrics the creator will receive from the viewers, such as how many likes the creator receives from the content from the platform. All right, so this is our causal name. Essentially, we're going to compare two quantities. And the first quantity is the creator outcome. Suppose every creator here gets the treatment. And that is every content items in a set here will be evaluated by the new recommender evaluation. And that is the treated evaluation here. And the second one is the critical outcome under the global control status, which means that everyone here will receive the status quo evaluation, and that is the global control status here. And typically, the platform is very standard. The platform will just run an A/B testing to evaluate the treatment, and that is to randomize the creators into a treated group and also the control group. And then a standard estimator under this design is the difference mean estimator, which just compares the averaging outcome between a treated group and a control group. Okay. But unfortunately, this one is biased. Why is that? Let's take a look at the constituent set here. The content A and content B, they are in the same constituent set, and they're both competing for getting exposed to the same viewer. And this kind of computation exactly captures how interference happens. But because we have the computation here, one content treatment status, which means that the evaluation method will affect how another content is being exposed, and that is exposure probability we are going to capture here. And that is named as the interference bias in literature, and essentially it's due to the cannibalization on the same viewer side, the demand side. With that, the standard condition, the suitable condition is violated, which is the validity behind the standard difference mean estimator. So that is why the difference mean estimate is biased. And as we see in the right panel here, we simulated different kinds of treatment during the ranking phase. And then you can observe that sometimes the difference mean estimator can have the positive bias, and sometimes you have a negative bias. And that is actually what we observed in practice. In our partners platform, we observed that if we run a criticized difference mean estimator and we compare that quantity with the treatment effect we measure after the full deployment, and actually you can see there's a huge discrepancy here, and sometimes they even change the sign, which means that will affect our decision making, and that is something we want to address in our work here. Okay. So this is our method, sketch here. We still use the data from the creator side randomization, which means that we don't really change the infrastructure of the experimentation here. But instead, we're going to propose a new estimator, which is the device estimator and the sample parametric, in the sense that we're going to use the choice model to try to rationalize the recommended behavior. And then we're going to use the machine learning tools to help us to capture the personalization and heterogeneity in our individual level data. And this is a quick look at the performance comparison between our method, which is depicted in the red line here, with the difference mean method, which is standard method depicted in the blue line here. And this plots the standardized error of different estimators and benchmarked with the standard normal, which is depicted by the black dashed black line here. And as you can see here, again, the difference mean estimator is biased, and our estimator is almost unbiased, but more importantly, it is asymptotic normal, which means that we can use our estimator to construct the valid confidence interval for our estimation, which is important for the platform because they want to know how confident we are about our estimation, such that they can control for the type error across a lot of experiments. All right, so we're definitely not the first one to look at the marketplace interference, and there are a bunch of literature here. The literature has seen two lines here. The first one is to propose new experimental design such that the treated groups and the control groups, they are not interfering with each other. This is costly in our platform, and so that is why we are not addressing the bias using a new design here. The second one is to propose a new method, a new estimator, and that is how our method here contributes. But that really requires we have a really delicate modeling of the interference. And for example, the different literature has been looking into the interference during the ranking stage, during the matching platform. And here we're going to focus on the recommendation and computation caused interference. All right. So I'm going to talk about our method now. This is how the data is generated on the platform. For each viewer query I here, we will observe the viewer embedding or viewer feature, which is named as the VI here. And CI here is the set of the features in the set of the items features in a constraint set here. And WI here is the treatment status and of the constraint set, which can be 1 or 0 for each item. And that is Boolean randomized treatment. And there are two phases in our modeling. The first part is to model how the recommender behavior. That is how recommender chooses the item from the constraint set. And here, for the chosen item, we use the notation ki star here. And the second part is the viewer response model. That is, given the chosen item, how the viewer is going to respond to the constraints to the exposed item, and that is the viewer response model. For the first part, we are going to, as I mentioned previously, the recommender actually evaluates each item in the constraint set, and that implies an implicit score we can learn from the data non-parametrically. And here we use the S-now here to denote the implied score under the old evaluation, like the status quo evaluation, that is our baseline score. And then after you apply treatment, the recommender will change the evaluation, and we use the S1 here to denote the score uplift due to a treatment. And both S-now and S1. Okay, so given the S-now and S1, then following a choice model literature, we can reconstruct the exposure probability. That is how what is the likelihood of each item being exposed to the viewer. And then we use the machine learning method, and in our context, that is the neural networks, to learn the S-now and S1 from the data, non-parametrically. And the second part here is fairly straightforward, which is just to model the viewer response. And here we apply again, we apply the machine learning method to learn how the viewer is going to respond to the exposed item ki star given the recommendation. Okay, so the Z hat here, we just learn it pretty non-parametrically, but essentially more generally, you can extend it to more complicated viewer behavior to capture maybe the sequential dependence among different viewer observations. And with the estimated nuisance parameters S-now, S1, and Z, you can do the counterfactual analysis and construct your first estimator, which is our direct plug-in estimator. We just plug in our estimation and to simulate what will happen in the global treatment and what will happen in the global control, and we can get our estimator. But okay, so here's the catch. The estimation of a nuisance can still affect your final estimation, and in fact, the estimation error of a nuisance parameter will prevent the plug-in estimator to behave asymptotically normal to allow us to construct the confidence interval we want to have. And in order to deal with that, we follow the double machine learning literature, which essentially constructs a new estimator by adding a device term here. The device term will make our new estimator not so sensitive to our estimation error of the nuisance parameters, and such that we can improve the device term here. After applying device term, our estimator, the final estimate, device estimate here is asymptotically normal here. And this property is known as the Niemann orthogonality condition in literature. Essentially, again, says that the estimation error of the nuisance parameter will not affect our final estimate that much. And with that, we show that our estimator is asymptotically normal with the estimated variance. But I want to comment on one final thing on our method here. The whole double machine literature actually builds upon the RAD samples. But here in our case, we have the correlated samples. And I can discuss offline why that is the case. But essentially, to address with the correlation among the data, we actually add an additional molecular analysis component to the proof to show that our estimate is still asymptotically normal here. Okay, this is the final part, which I'm really excited about, and that is we run a few experiments to justify our method. So for those of you who are familiar with the interference literature, one key challenge here is the ground truth, which means that we don't really know what will happen in the global control versus global treatment. And in order to get the ground truth, our partners think again, we run a really expensive experiment to justify our method. So essentially, we split the world into 3 separated universes. And in universe A, we run our standard experiment, which is the quantized randomization here. And based on the data there, we can construct the difference mean estimator as well as our device estimator. But in universe B, we apply the global treatment, which means that everyone here receives the treatment. And then in the universe C, we apply global control, which means that everyone here receives the control status. And then by comparing the outcome from the universe B and universe C, we can see that we can estimate our ground truth of the global treatment effect. And there's no interference bias between this estimator because the universe B is not interacting with the universe C, and such that we can construct our ground truth here. And one important component in our method is the choice model. And although our method is not designed specific to any specific recommended algorithm, but we indeed leverage the built-in machine learning algorithm to fit our choice model. And our model actually has a pretty good fit with the data. Like this is the ROC curve of our fitted choice model. And here is our empirical results. We are looking at 3 different outcomes here, and all of them share the same choice model. And the green bar here are the ground truth, and the green bar here are given by our estimator. And the red bar here are given by the standard difference mean estimator. And as you can see, okay, for the third one, for the outcome 3, everyone is aligned with each other. But for the outcome 1 here, both our estimator and the device estimator, they are like the ground truth and our device estimator, they show no significant result. But the difference mean the standard estimator shows the positive result, which is even worse for the outcome 2. So both our estimator and the ground truth, we show the negative treatment effect, but for the standard difference mean estimator, it actually shows the positive treatment effect, which means that if someone is going to make a decision based on the outcome 2, it's going to be a false decision. Okay, I'm going to skip the conclusion part to save time for the question. Thank you.